So I want to tell you a little bit about the subject of wave dark matter. Basically, dark matter as waves instead of particles, in some sense, even if they are fundamentally particles. The work is actually done with a large number of collaborators. You can see here. I would say probably the introductory part of the talk is based on the first paper with Jerry Oestreicher, Scott Tremaine, and Edward Witten. And I think the bulk of the talk will be based on the fourth paper. Is with Austin Joyce, Michael Landry, and Cindy Lee, and it's on the subject of vortices. And depending on whether we have time, I might touch upon two more recent papers, but it depends on whether we have time. If you're interested in more background, I recently completed a review for the annual review of astronomy and astrophysics. You can find that on the archive. So let's get started. I don't think I need this slide at all for this audience, so I'm just going to skip it. You all know there's dark matter. There's so much, the evidence is very overwhelming and compelling. Nonetheless, we remain very ignorant about its basic properties, right? And one illustration of our degree of ignorance is just the mass of the particle. If it were a particle, what is the particle mass? And it ranges over in this enormous range, right? All the way from 10 to the minus 22 electron volts. In this talk, when I say ultralight, that's what I mean, something close to that kind of mass. 10 to the minus 22 electron volts, and going up all the way to basically astronomical masses, right? Tens of solar mass. This enormous range. Now, there is actually one interesting mass scale in this vast spectrum that you can actually put down, and it's a kind of a nice, if you want, a nice demarcation point, if you want. And it begins by just asking ourselves, actually, what do we know? Well, we do know the following. We know the mass density of dark matter. For example, in the solar neighborhood, is this number 0.3 GeV per centimeter cube. Maybe slightly unfamiliar units. But given this number, you can ask the following question. At what particle mass would the interparticle separation be less than the de Broglie wavelength? Okay, maybe a little bit of an unusual question, but you can ask it. And given the observed mass density, there is actually a well-defined mass. The de Broglie wavelength, just to remind ourselves, is 1 over the particle momentum. So it depends on the velocity of the particles. And in this talk, mostly I'll be using velocity of basically in the Milky Way, 200 kilometers per second. Okay. And if you choose that kind of as a typical velocity, you can convince yourself there is a mass scale which is around 30 electron volts. If you are less than that, then you are in what I would call the wave regime. You are in a regime illustrated by basically my little cartoon here. You are in a regime where if you draw a sphere which has the size of the de Broglie wavelength, inside that sphere, there are many particles. If you are less than this 30 electron volts, you are in a regime where the de Broglie wavelength exceeds the interparticle separation. And this is what we could call the wave regime. I think of this as the analog of something very familiar. For example, in electromagnetism, if you have a stage with many photons, a lot of the times, not all the times, but a lot of the times, you can actually treat it as basically a system of classical waves, as you know, or classical fields, electromagnetic fields that we learn in classical ENM. And here we are interested in a similar kind of situation, okay? Less than 30 electron volts is the wave regime. By assumption, I put the word bosonic here. By assumption, to have multiple particles in the same de Broglie volume, these particles must be bosonic. Otherwise, exclusion principle would forbid you from doing that. So we're talking about bosonic particles. And in this talk, I'll be focusing mostly on spin 0 scalar particles, although a lot of the phenomenology carries over to spin 1 or spin 2 in 1. To just give you a sense of scale, the Brody wavelength, I give you kind of 3 different kind of numbers just to have some concrete numbers in our mind. For the ultralight, often called fuzzy dark matter, the Brody wavelength is truly astronomical, a sizable fraction of a galaxy, and as you can imagine, could have some fairly dramatic consequences, which we'll talk about. I also put down a number that is still rather light, but for the purpose of this talk, I will only call it moderately light. 10 to the minus 6 electron volt is in fact the target mass of some axion detection experiments. If you translate to the Brody wavelength, it's actually not that small. It's not astronomical, but it's actually not that small. It's some fraction of a kilometer. And it turns out the wave phenomenology would actually have some consequences for axion detection experiments, as I will explain. Okay, so let me give you kind of an outline. I would probably spend, I hope, maybe 5 minutes on particle physics motivations, why we might want to investigate a particle with this kind of mass, less than 30 electron volts. Most of the talk, I will be talking about how the wave dynamics actually work and the phenomenology, what it implies, especially about astrophysical implications. But I hope I would have time to get to also experimental implication, and by experimental, I mean axion detection experiments. If you are in the ultralight regime, then you have the possibility that the phenomenon associated with waves is actually observable by astronomical means. If you are just in the moderate light regime, it would be hard, but there would be implications that are important for detection experiments. And once again, these are the mass scales that is good to keep in mind, and the length scales. In the ultralight regime, as I said earlier, it's often called fuzzy dark matter, coined by this set of authors, Hu, Bakana, and Gruzinov, in a classic paper. 10 to the minus 6 is one possible mass for the QCD axion, although there is actually a rather large range for the QCD axion also. Okay, so let me start with particle physics motivation. And by the way, I wouldn't mind at all if you interrupt me. In fact, I think it helps. So please do interrupt me if you have any questions. And I'll pause from time to time to ask for questions in case you have any. So particle physics motivations. A fairly natural candidate for a light scalar particle would be what we would call a pseudo-Nambu Goldstone boson. A Goldstone boson, a strict Goldstone boson should be exactly massless, as you might know. This is not a strict Goldstone boson, it's a pseudo-Goldstone boson. To kind of just remind us how it works, imagine you have a theory that have a rotational, a U1 symmetry. This is the potential for the scale, for some scalar. The set of vacua, which is basically this circle down there, breaks basically, if you choose any one particular value, would break the symmetry. And the excitations in the angular direction, if you want, which I'm going to call phi in this talk, is basically the Goldstone direction. And just imagine this Mexican head potential is slightly tilted, and it gives the particle a small mass. And it turns out this is something that happens fairly generically, that even though at the level of perturbation theory, what you should have is a strictly massless particle, very often non-perturbative effects think of it as the analog of quantum tunneling, often generate a very small mass. Okay, and the most famous example is, of course, the QCD axion. Unfortunately, I don't have time to go into details of that. There are also a lot of what I call axion-like particles in more general settings, such as in string theory, where these particles are associated with having extra dimensions, and you have the analog of color-cycline modes. Now, I do want to kind of add a footnote to this just general, very broad stroke in motivation, which is kind of specific to the ultralight mass. What am I talking about here? Sorry about this kind of a little bit of a busy slide. I want to just give a little bit of a motivation for a very light mass. And it comes from thinking about the abundance of dark matter. And the story, roughly speaking, goes as follows. Again, in this top 5 is the axion. This is the potential that is generally generated, as I said before, by some non-perturbative effects, instanton effects, which generally is very suppressed, very small. This angular field phi, if you think of it as an angle, it has dimension of energy. And there is an energy scale associated with that periodicity, if you want. And that energy scale is often called axion decay constant, denoted here by F. And the fact that this is a cosine is not an accident. It's basically because this is kind of like an angle, an angular field. And if you expand out the cosine, assuming small phi, you can read off from the quadratic term the mass, and it goes as follows. And basically in this story, because this lambda, this energy scale is fairly suppressed, usually exponentially suppressed, because it's a non-perturbative effects, this mass can be rather light. So that's kind of the motivation behind thinking about small mass if you want. But why this particular number? It comes from thinking about what happens, actually how you generate the dark matter abundance to begin with. So imagine here I sketch out the potential, right? This is the potential for the scalar, which is basically this potential. Imagine in the early universe, the scalar has some primordial value, and for the lack of any better idea, we assume that the scalar field, this axion, has a primordial value, which is of the order of basically the only scale, the axion decay constant, the periodicity scale. So in the language that is often used, people will say, oh, your misalignment angle is order 1, meaning phi over f is order 1. Imagine that is true. And in the early universe, the Hubble expansion rate is pretty fast, and Hubble friction would just basically lock the scalar field at this value until when the expansion rate slows down enough so that the Hubble expansion is of the order of the mass of the particle. Just to give you a sense, if the mass is indeed this size, you basically reach this kind of scale at a redshift of around 1 million, something like that. After that, basically the Hubble friction is no longer effective in locking the scalar, and the scalar would basically start oscillating around. And as you might recall from your quantum mechanics or quantum field theory class, these oscillations you can interpret now as a set of particles if you want. And you can actually check the energy once the scalar field oscillate close to the minimum, which in general happens just because of Hubble friction. Hubble friction takes away oscillation energy. So the oscillation amplitude will be closer and closer to the minimum. In fact, it's sufficiently close that you can even forget about this cosine. Just think of this as a quadratic potential, m squared phi squared. And then you can convince yourself the energy in the oscillations, redshift like 1 over volume, just like energy in a set of non-relativistic particles. So this is a good dark matter candidate from that point of view. And skipping some steps, you can actually show what is the radial abundance today. Okay, so the radial abundance is roughly what you need to match the known dark matter abundance. If the axion decay constant is rather large, 10 to the 17 GeV, which is somewhere between gut scale and Planck scale, turns out to be fairly generic in a lot of the string theory constructions. And importantly, the mass is rather light, 10 to the minus 22 electron volts. If you like this coincidence, if you want, the fact that you can match the observed abundance of dark matter with this relatively simple story, at least is one motivation for thinking about light dark matter particles, in fact, ultralight, 10 to the minus 22. That being said, though, one should not be too attached to this particular number. Don't be overly attached to that number, because by this argument, in fact, the radial abundance is more sensitive to what you assume about this fundamental energy scale, the axion decay constant, because it goes like that square, as opposed to the mass, which only is kind of, in some sense, the dependence is weaker, mass to the 1/2. Nonetheless, it seems like a reasonable motivation to at least think about dark matter particles that are rather light. So that's my very quick motivation, if you want, for thinking about light dark matter particles. All right. You can also just be completely agnostic and just say, well, you know, the dark matter particles can be above 30 electron volts or lighter. Let's just consider the lighter option and see how far we can understand what's going on and what kind of predictions we can get. Okay. Let me just pause here before I now move on to the phenomenology and the dynamics, in case there are questions. I cannot see chat, so if you write in the chat, maybe Kelly can let me know if you see anything.
I don't see any hands or chats yet.
Okay, otherwise I'll just keep going. Do interrupt me if you have questions. So the dynamics actually is very simple. The equations are very familiar ones. So as I said earlier, your oscillation would be pretty close to the minimum after several eVols of expansion, once it starts rolling down basically the potential. And so you can basically treat this as a free scalar. It's a free scalar with a mass. This is the Klein-Gordon equation. For application to large-scale structure and galactic structure, we are interested in what happens in the non-relativistic regime. And it's a very standard thing in that case to rewrite your Klein-Gordon scalar phi, basically our axion, our angular field, if you want, which is a real scalar field, in terms of a complex scalar field, which is called psi here. The trick is basically the following. If you see this mass here, you can convince yourself in the non-relativistic regime, mostly what it means is your phi must oscillate with frequency m, which is shown here. By the way, everywhere you might think there should be an h bar, I've set that to 1. So those things are all well hidden. So the frequency m, you can see basically from the Klein-Gordon equation. So the non-relativistic approximation is to factor out that time dependence and say whatever residual time dependence in the wave function psi, I'm going to call it wave function, and you'll see why in a moment. Any leftover time dependence on psi is rather weak. Basically occurs on much longer time scale than 1/m. In that limit, you can convince yourself that the Klein-Gordon equation become actually the Schrödinger equation, written like this. It really is the usual Schrödinger equation that you're familiar with, where psi plays the role of the wave function. There is a potential here, and the potential is important to include because here we want to include only one interaction, which is the gravitational interaction. So this phi is the gravitational potential. And I draw this little wiggle here to remind us that here what we are talking about waves, and I want to emphasize what we are talking about here are actually classical waves, meaning think of these as the analog of electromagnetic waves in the same sense. Despite the appearance of a Schrödinger equation, think of the wave function, even though I'm going to call it the wave function. Think of this as just a classical wave, just the same way you would think of as, you know, E and B fields, basically. The system of equation, there are only two. One is this equation. The other equation is basically Poisson's equation. It tells you the gravitational potential is sourced by what? Sourced by basically the density in these particles, which is nothing other than what I wrote here. Is the mass times psi squared. Psi squared is the number density of particles, what you might expect. And so that's it. In terms of equation, it's actually a very simple system. You have Poisson's equation that tells you how gravitational potential is sourced. And then you have the Schrödinger equation that tells you how this wave or field evolve in time, following Schrödinger equation. Now, for conceptual understanding, it is sometimes useful to think of this as a fluid. That's what we often do in large-scale structure. And as a fluid, it's useful to keep in mind your wave function is a complex quantity. It has an amplitude and a phase. The amplitude you can interpret as square root of density, right? Because again, the density is basically psi squared. So the amplitude is square root of density. What about the phase? The phase turns out you can interpret as a velocity potential. So if you interpret as a fluid, the fluid velocity is 1/m times the gradients of the phase. And you can convince yourself this identification actually makes a lot of sense because it turns out, recall in quantum mechanics, you might recall, there is a conservation law, which is conservation of probability, if you want. In the fluid interpretation, is actually conservation of mass. Or to put it in even more mundane ways, look, what we have is a set of particles, non-relativistic. You're not creating particles, you're not destroying particles. Particle number is conserved. And that basically this expresses that, mass conservation. And the Schrödinger equation, of course, is a complex equation, so there should be two independent components. The first component, if you want, is mass conservation. If you try to interpret it as a fluid, there is a second equation you could write down, which is basically in fluid mechanics, you would call it the Euler equation. On the left-hand side, you have basically acceleration. On the right-hand side, you have gradient on the gravitational potential, which accelerate particles as you expect. The last term might look a little bit unfamiliar. In the literature, it's often called quantum pressure. It's a bit of a misnomer because what we have here is actually neither quantum nor pressure. It's not quantum because, again, I want to emphasize we are really just talking about classical waves, just like classical EMF. And actually, if you actually pay close attention and compare to the usual Euler equation where here there might be a pressure term, this actually is not exactly the form of a pressure. Nonetheless, I'll use that term, and there are aspects of it which actually make it behave like pressure, as you will see. Okay. Any questions before I go on? These are basically all the basic equations that you need to know. The rest is you can actually argue more or less from qualitative arguments. Right?
I have a quick question, Lam.
Please do.
Yeah. In what sense, if it's a fluid in the sense of like, say, a superfluid, of course, coupled to gravity, in what sense are we thinking about it as a particle? Because we have to now think about the excitation of the fluid, or it's not necessary to think that way?
Yeah, you can think about extraordinary fluid. So fluid, as you know, has sound waves and things like that. And here you can think of this fluid as having sound waves. Yeah.
Thank you.
Yeah. By the way, even in the particle regime, let's say we have dark matter particles and they are actually heavier than 30 electron volt that I was talking about. So you are actually in the particle regime. If you coarse grain sufficiently, there would still be, in some sense, some kind of waves. What is interesting here in the wave limit is because essentially this last term, quantum pressure, is actually non-negligible. You have kind of additional wavy effects that you would not see in the particle limit. In fact, actually, this way of writing is helpful because, look, this term, if you take m to be very big, become very small, and you can neglect it. And this equation is really just the equation of, a pressureless fluid, which is how you usually will model large-scale structure. So in the large mass limit or in the large scale limit, if you want, this term is negligible. And in this talk, we are precisely interested in the opposite. We are interested in cases where this term actually plays an important role. Yeah. Thanks for the question. Okay, so I think I can skip this. Here I'm just citing authority, citing Feynman, but you can actually find the same equation I showed you here, which might be a little bit unfamiliar looking, but I suspect you have actually seen this before if you have read Feynman. This is in volume 3, the last chapter. You can find the same equation. Okay, so I just want to say, I'm not giving a lot of references here, but the subject of scalar field as dark matter actually has a very long history. There are plenty of papers here, so I just want to give this literature credits, and specifically thinking of dark matter as superfluid. There's also a literature on that, so I also want to put this out here. The main difference, if you want, in what I'm going to talk about, if you really want to think of this as describing a fluid or a superfluid, the version that I have in mind that I'll be focusing on is, in some sense, the minimalist version. Minimalist in this sense, so let me go back here. Minimalist in the sense that, look, this scalar really is fundamentally what I start with is just a free scalar with a mass. It doesn't have any interaction other than gravitational interaction. Whereas in the literature, in the earlier literature, very often the focus is on a regime where this scalar, the axion, actually have non-trivial self-interaction, for example, non-negligible one. And here in the talk here, mostly we are in a regime where that is actually have kind of relatively minor or negligible effects. So it's kind of the minimalist version of, if you want, of superfluid dark matter. Okay, so let me just play a little bit movie here. What are these wave effects I'm talking about? Well, I hope this movie kind of make it very clear what are the wave effects I'm talking about. No, I should say this is not a movie in time. Don't interpret it as a movie in time. This is really just one snapshot in a cosmological simulation where we just cut slices across the box. I'm just showing you that those slices. But what you can see very clearly are wave interference effects, no? And that is really the first thing that would jump out at you, the fact that fundamentally what you have are waves, and imagine you are, for example, one of these halos, no? And inside the halo, instead of having, a bunch of dark matter particles or stars orbiting, now you have a bunch of waves sloshing around, and they have somewhat like random phases. And just by chance, there will be places where you have constructive interference, and there will be places where you have destructive interference. It's kind of an inevitable consequence of having waves. And that's basically what you're seeing here. You have this interference pattern, not only in halos, but also actually in filaments. And the rest of the talk, I will be really basically focusing on these aspects, basically these interference aspects. What does that mean? Can we observe it? I should say there's been a lot of work on basically this aspect of the wave phenomenology. I list some of the reference down here. And the first paper that actually make this very clear, that's a really nice paper, is by Shive and company. Okay, let me go ahead. There are a lot of effects to talk about. Unfortunately, I don't have time to talk about them all. I'll be happy to discuss any particular topic. I'll be focusing on more recent work that we have done. In particular, I think, given the amount of time we have left, I think I'm mostly focused on vortices. I might mention 1 or 2 slides on the next 2 topics. I don't think I have any time to talk about accretion around black holes. So I'm mostly focused on this. Some of you probably would be interested in hearing about what are the current constraints. I don't really have time to talk about that here. However, I have prepared 1 or 2 slides on current constraints. So if you are interested in that, ask me about it towards the end. I can show you, kind of give you a very short summary. Okay, so I'm going to start with vortices. Okay. At first sight, you might actually wonder why I even am interested in vortices, right? Because vortices are places where the curl of the velocity is 0. And I just told you in the fluid formulation, the velocity is pure gradient. So the curl by definition is just 0. There should be no vorticity. It turns out actually there's a loophole, or if you want, there's a breakdown of the fluid interpretation. And the breakdown is actually a very simple one. Think about the wave function, this wave function, complex wave function. And again, there is an amplitude and a phase, right? Let's just imagine of all these complex interference patterns that you might have in a filament or in a halo. Occasionally, just by chance, there would be complete destructive interference where the density go all the way to 0. Now, let's think about those places. Those are the places where the phase would become actually ill-defined. And it turns out this kind of like sounds like a fairly minor loophole, but it turns out this loophole actually allows you to have what we would call vortices, as you will see. I want to show that to you in the next slide. It turns out these are places where the velocity actually flow around in a circular pattern, really like vortices in a superfluid, which you might have seen before in the case of superfluid helium. Now, that being said, you might respond that these places where just by chance you have complete destructive interference, where the density is actually 0, seems like rather ad hoc and probably rare. What I also want to show you, I'll postpone that for maybe 5-10 minutes, but eventually I hope to get there. What I want to show you is, in fact, they are not rare at all. In fact, in the late universe, this inside a halo, like the Milky Way, for example, is actually rather common. That's what I want to show you also. So it's kind of a generic prediction of having wave dark matter. And let me just make kind of a qualitative remark here. Maybe I'll come back to that later. Of course, we have waves in the early universe too. No? In the early universe, we have waves, just like in the late universe. However, in the early universe, remember the fluctuations are very small, right? 10 to the -5 fluctuations. So you have a homogeneous fluid or wave function with 10 to the -5 fluctuations. Even if they interfere, the density can never go all the way to 0 because the fluctuations around the mean is 10 to the -5. You cannot have the density go all the way to 0. It's just exceedingly unlikely. However, if you let gravity do its work, over time, the fluctuations get amplified to order 1 or bigger in the nonlinear regime. Then you have large enough fluctuations that destructive interference can actually drive the density all the way to zero. So this is really an effect due to gravity, amplification of fluctuations until you can have destructive interference. So it's really a nonlinear phenomenon. And interestingly, it actually happens generically. That's what I want to show you. Lastly, let me just make a comment. A lot of what I'm going to tell you about vortices are actually well known in the condensed matter community. If you like the main, if we can claim any novelty at all, is that this is a situation which is slightly unusual, if you want, is where vortices form as a result of gravity, which you usually don't have in condensed matter physics. So what am I talking about? So here are a few points. I think this is the main slide where I have at least some detailed arguments. They are all pretty, I hope, intuitive, but let's go through it slowly. First of all, let me try to convince you what these vortices would look like in three spatial dimensions. Remember, we are interested in the set of points where both the real part and the imaginary parts of the wave function vanish, right? Now imagine you have three spatial dimensions and you ask yourself, generically, where are the set of points where the real part vanish? If you think about it, it should form a surface. And likewise for the imaginary part. So you have some surface in three spatial dimensions where the real part vanish, and you have another surface where the imaginary part vanish. Where they cross is where you have both vanish. And so generically, but just by that argument, you know, the set of points where the wave function vanishes should form a line, basically, okay? And in fact, you can actually further show, I'm not going to show here, that line cannot somehow just end. They are kind of like magnetic fields, so they should form a loop. So, and as I will argue in a moment, they should form what we call a vortex ring. Now, let me show you a segment. No, this purple line is supposed to illustrate. Okay, just imagine in our head, these are the set of points where the wave function vanishes, both the real and the imaginary part. And now let's ask ourselves, well, how should the phase the wave function behaves when you walk around a loop around that line? Well, the wave function has to be single value. So if you wrap around that line, the phase must wrap around by integers of 2 pi. It has to do that. And what that tells you is that, remember this, away from this line where the wave function vanished, the fluid description is completely valid and fine. And remember, the gradient of the phase is the fluid velocity. And the fact that the phase wraps around actually tells you you have non-zero velocity circulation. This fluid velocity, if you integrate around a loop, would have these basically quantized, values. Basically, integers of 2 pi over m. M is the mass of the particle. Okay, so rather dramatic prediction. It would be nice if we can directly observe the velocity of that matter, because if we could, then this is it. If you see it, then you know, okay, there's no escape. This is something that behaves like waves. Unfortunately, we do not observe dark matter velocity directly. We can only see it indirectly, and so we have to do more. We have to be more clever in deducing what's going on, as you will see. So this is one thing that generically you will get, and the name vortices, I hope, is pretty well motivated by now, because we really have non-zero velocity circulation around such objects. And you can think of this as topological defects if you want. Hence I call it a string defect. In fact, you can say more by actually very simple argument. I already argued these are the places where the wave function vanished. So let me call that x equals 0. Just pick a point along this purple line, x equals 0. The wave function vanishes. And I move a little bit away from that point. Well, I can do a Taylor series expansion, right? And the first order term would look like this. And now recall the density is the wave function square. So this immediately tells you, as you move away from a vortex, the density profile is completely predicted and generic. It goes like R squared. It vanishes at R equals 0 where the vortex is, but it grows like R squared. Similarly, if you think about this velocity circulation, this is a constant on the right-hand side. The loop you can make bigger and bigger. And so for this to work out, the velocity must drop by 1/r. So these are completely generic predictions without actually assuming a whole lot, actually. All you need is to have these waves. And lastly, you have vortex ring, as I talked about earlier. Just a word here, the vortex ring here should be distinguished from what are usually called axion strings. Those are two different things. I can talk more about that if you're interested. Okay, let me show you some pictures. Do we find these things in simulations? And the answer is yes. In fact, I'm going to skip this one even. I'll just go straight to these. So this turns out, I'm not showing the halo here, but this is a halo that you form from gravitational collapse. And you can just go to this halo and I try to identify these vortex rings, and they are here. You can see them very clearly. I highlighted them. The key to finding these things in the simulation is not only to look for low density, right? Because these vortices are where rho is 0. And as you can imagine, in the simulations where you have numerical noise, you can never be sure something is actually exactly 0 anyway. The more robust thing to do is to check the velocity circulation. You actually want to check the winding around these things is actually these integers of 2π. So that's how actually you find these vortex rings. And in fact, generically, we found higher winding is very unlikely. Mostly you have single winding. And what I call n is ±1, basically. In case you think these vortex rings are always these nice circular things, that's not true. This is a very symmetric, spherically symmetric halo. A more realistic halo is more messy. You can check density profile. It grows like distance square. I showed you earlier. You can check the velocity profile, drop by 1/r. So all these things checks out. There are simple solutions. Let me just not go over that, except just to say these vortex rings, they are very dynamic, meaning they usually don't stay put. In fact, in general, if you have a ring like this, it would actually move. In fact, the velocity scale with the size of the ring. The smaller the size, the larger the velocity. And in fact, these rings, not only do they not stay put, they can actually appear and disappear, but the only way they can appear and disappear is by, for example, starting from a very small loop. You can nucleate them from a small size and then grow to a big size. And then they can only disappear once they shrink back to a small size or collide with another loop, basically. So you can think about all kinds of fun scenarios where these things interact. This is actually how the velocity flow goes. If you work out the dark matter velocity flow around a ring, it goes like this, but the ring as a whole has a bulk motion, which is inversely proportional to the size. I think I'm going to skip this movie in the interest of time. And a few comments, right? And this circle back to the comment I made earlier. Should these defects be rare? And the answer turns out to be no. I have to say, when we started, I thought for sure these objects would be fairly rare because you need complete disruptive interference. It turns out they are actually not rare at all. Generically, you expect one vortex ring per de Broglie volume. Okay, so depending on the mass of the particle, the Broglie volume, of course, scales with that. But If you fix the mass, you know that the body volume, you always have on average one vortex or vortex ring per the body volume. So these are actually ubiquitous. And you can actually show that this is true both analytically and just by checking out simulations and looking for them. And we have done both. I already talked about this. Small rings move faster, or curved segments move faster. I also alluded to the fact that these vortices, they are actually transient phenomena. These are transient things, meaning they change with time. You can associate a coherent time scale to them, which is actually also fairly intuitive. You just basically estimate what I call the de Broglie time. Essentially take the de Broglie wavelength, which is 1 over mv, and divide by n to the power velocity. That gives you a time scale. That's called the de Broglie time. And to give you a concrete size, if you are in the ultralight regime, the de Broglie time is actually very long, billions of years. So these things actually stick around long enough to produce perhaps interesting astrophysical signal. Okay.
So Lam, it's 4:20, just wanted to let you know, and folks definitely are interested in any constraints or promising avenues for detection.
Fantastic. That's what I'm going to get to now. Let me skip this plot. Let me go to constraints, right? Observational signatures. Well, what are the observational signatures? Essentially, the interference, constructive and destructive interference that you have in a wave dark matter halo means you have substructure. And so the usual methods that you would try to look for CDM substructure, you can imagine you can translate them into this case, essentially, but you should keep in mind, this substructure is quite different. They are not in the form of a stable subhalo, very light subhalo. It's not like that. In fact, it's in the form of these basically interference fringes, the Broglie size. Sometimes the density can go all the way to 0, rather dramatic, and it's transient, it changes with time, okay? And among the possibilities, I don't have a lot of time to go through the possibilities. Ken is here. Ken has worked on thinking about looking for, here I said vortex, but really what they had in mind is more general substructure by thinking about gravitational lensing. There is another gravitational lensing, which is basically looking for what we call flux anomalies, which you probably have heard of, right? When you have two highly magnified images close to the vertical line, if there is no substructure, the two images should have same magnification. If there's substructure on the scale of the image separation, it would cause relative magnification between them, and it's something you can look for. The conservative estimate is that for high magnification events, like around 100 here, this is one example from the paper from Dye. Conservative estimate is you can have relative magnification from substructure, this kind of interference substructure at the level of 10%. It could be bigger. So that's one way you could look for these things. Another way is to think about scattering of tidal streams. There was an earlier paper by these two authors. We also have a recent paper. I'll just show you a little picture here. This is a numerical experiment that we did with Neil Delau, Joe Brophy, Siyu Lee. And essentially, basically, if you have a stream moving around, circling in the Milky Way, let's halo, let's say, over time, scattering would cause the streams to be not smooth. And in fact, in general, generally, it will fall upon itself to form caustics. And these are observable things. And the lighter the dark matter particle, the more observable it is. Okay. Let me end with some words about experimental detection. So this applies in the case not so much for fuzzy dark matter, but for moderately light dark matter particle, QCD axion, for example. Typically, those experiments look for relies on basically coupling of the axion to either to E and M. FF dual is basically E dot B, or the coupling of the axion to the spin of fermion. Psi is basically fermion. You can think of those as electrons if you want, or quarks, or nucleons. And essentially different experiments measure different combination on phi, you know. Some of them spatial gradients, some of them time gradients. The main message I want to get across without getting into detail of these experiments is the following, and I think it's an appealing way to think about it, especially if you have an astronomy background. What we have fundamentally in a halo is that because you have waves, a set of waves with random phases sloshing around, what you have is really a stochastic field. It's a stochastic signal. Imagine you have a detector at a given location. What is the signal that you will see? This is the wave function. This is the axion field. At a given location, your signal as a function of time will probably vary something like this. This is the rapid oscillation at the axion mass. There will be longer time scale modulation, which is basically due to interference. This is the coherence time, 1/mv squared, due to this interference. And this interference pattern, if you want, again, they are transient. And the most helpful way, in my view, to think about axion detection experiment is you are really trying to get at the two-point correlation function. Because you have stochastic waves, really, you should think of your experiments as if you want some kind of interferometer. Think about radial interferometry. In fact, not only should you measure two-point function with a time lag, you can have detectors at different places and measure space-time correlation function, really like a radial interferometer. And in fact, there are fairly generic predictions you can make about the space-time correlations. I don't have time to talk about that. At vortices, let me just say, at vortices is very interesting. If you happen to have a vortex that passes through your detectors, phi would be 0, as I said earlier. The field would be 0, but the gradient actually is not. So some experiments will see 0, some experiments will not. Depending on how you're measuring the axion. Perhaps most kind of interesting in my mind is something we are actively working on, is that the existence of vortices is actually telling you the axion field has a very interesting spatial structure, if you want. If you express it in terms of the wave function and its phase, which is this theta, it tells you the oscillation in time of the axion field. This phase has interesting space-time structure. The question is how to capitalize on that to do better measurements. I think I'll just leave it as that. I think I'll conclude. How much time do I have? I have maybe 1 or 2 minutes.
Yeah, we've got a couple minutes.
Yeah, okay. Let me just tell you, this is more recent work. The fact that you have interference actually tells you there are funny things that would happen. For example, we know in a wave dark matter halo, the center of a halo, this is a density profile, they often have a fairly prominent core, what is often called a soliton. What is interesting is because actually fundamentally you have wave interference, this core actually refuses to stay put. So this is actually a simulation that we did. And these are different snapshots in time. This is just the initial condition, just a bunch of halos that are going to merge. The cross here is the center of mass. The highlighted red stuff is that soliton core. And you can see over time it's actually wander around, move around. And that is actually also an inevitable consequence of wave interference. It has to random walk around by an amount of the order of the size of the soliton or the Brody wave. I'll be happy to talk more about that. And let me skip ahead to a conclusion. I think we are just about time. If anything, I just want to have a very basic message across, right? Is conceivable that matter particles might be lighter than 30 electron volts. In primary example from a particle physics point of view would be some sort of axion or axion-like particles. But you could be even more open-minded than that. But the point is, if you're lighter than that number, wave phenomena are basically unavoidable. And so there are all kinds of fun phenomena to explore. In the limit that the particle is actually ultralight, there would be astronomically observable things. In the limit that is not ultralight but moderate light, it will still have implications for axion detection experiments. And I talked very briefly about the creation of caustics in tidal streams and the fact that solitons, I didn't talk about oscillation, but they oscillate and also random walk. Unfortunately, I didn't have time to talk about black hole here at all. But I think I'll pause here. Thank you.
All right, thanks so much. Are there any questions for Lam or topics of discussion? I think we're few enough that you can go ahead and unmute yourself. Go ahead, Ken.
Hi, Lam. Thanks for the very nice colloquium. I had just a question about the vortices.
Yeah.
So as far as I understand, it's sort of an irreducible consequence of a real scalar field, right? That you have these vortices. So what about, is there something, does this vortex description allow you to understand things better about fuzzy dark matter? Or, yeah, that's the question.
Well, I would say, yeah, it's a generic prediction that whenever you have waves, you have destructive interference. And if those waves has random phases, this would happen at the frequency of 1 per the Broglie wavelength. So those are pretty generic predictions. And I think probably in terms of what you learn from this are kind of like the generic predictions. For example, you know the density profile. That's a generic prediction, is this R-square profile. And one might hope that if you want to devise a way to observationally see these things, knowing a generic profile would help you kind of pull this out of noisy data. That being said, though, I have to say, to qualify a little bit what I said, from everything, from at least the situation we have thought about, an isolated vortex ring seems a bit hard to detect on its own. The signal is actually rather small. So the signal that I talk about, like scattering of tidal streams, even the gravitational lensing, mostly they are really the cumulated effects along the line of sight, if you want. For example, in the case of lensing, of like constructive and destructive patches. So it's not really just isolating one vortex. There, in principle, is possible. In practice, the signal is small. So we haven't come up with, if you want, a way to really just isolate one single vortex. That would be nice, because if you can verify for a single object this R-square profile, that would be a pretty, that would be at least a pretty good supporting evidence that this is what's going on. I don't know whether that answered your question.
Yes, thank you.
John?
Hi, thanks for the beautiful talk. I have a very naive question, which is that if the velocity goes as 1/r away from the vortex, what happens as r goes to 0?
That's an excellent question. So what happens is this, you can ask yourself, at what radius would that velocity go to the speed of light, for example, right? And it's actually very easy to check. That happens when you go to the Compton wavelength. So not the Broadway wavelength. The Broadway wavelength is 1 over mv. The Compton wavelength is 1 over mc. C is the speed of light. So that's much smaller scale. So basically, when you go to that kind of scale where you're at Compton scale, one probably should not use the wave function description, the non-relativistic description anymore. Probably it's more helpful to revert back to the original axion scalar description. So if you ask what is going on, nothing crazy is going to happen. There would not be some faster than speed of light travel or anything like that. Yeah, it's a good question though.
And Joshua.
Yeah, thanks for a very good talk. So I'm actually curious about the black hole part, so was wondering whether you can give a few comments on it.
Sure, I can. These are basically some constraints. By the way, if you're interested on kind of existing constraint, you can look at a review I put out recently. But let me skip ahead. So I'm going to just play a movie, actually. That probably is the most helpful thing to do. So this phi is that scalar. And this is radius. And here, by radius, I do not mean the usual radius in Schwarzschild coordinate. This R star is what is called the tortoise coordinate. And large R is basically the same as the usual R. But the horizon is actually mapped all the way to negative infinity. So far right, okay, you are very far from the black hole. Close to the black hole, you'll be going in the negative direction. And now imagine you have this scalar field oscillating far away. That's your dark matter particle. What would that do as you go closer to the black hole? I'll just play this movie. This is what's going to happen. It would set up waves. These waves would actually travel into the black hole. In the process, you can see this wave actually get magnified in amplitude. What is going on actually is actually fairly mundane, you know. It stands to reason if you have stuff around the black hole, they can get accreted onto the black hole. This is all there is to it. This is just black hole accretion, except that it's accreting not particles, but it is accreting waves. And in the process, these waves get magnified, and you can actually predict how magnified they are.
I see.
Yeah.
So this is basically assuming this is a Schwarzschild black hole, and it's going to preserve the same thing even if you have a curved black hole.
For a curved black hole, there would be actually, there could be more possibilities. At a minimum, you also have this accretion. But in some cases, you can have more exotic possibility. You might have super radiance and so on.
Right. Yeah, I see. Thank you.
Thank you.
Go ahead, Colin, sorry.
Yeah, just a quick one. Thanks, Lam, for this great talk. I was just wondering if you thought about any possible connections between this fuzzy dark matter scenario and this recent, let's say, tentative evidence of cosmic birefringence in the CMB. Yeah,
that's a great question. There probably is a connection. I have not looked carefully, though, at the, for that CMB signal, to explain that signal, how big an axion decay constant do they need? Do you know? Would you happen to know?
They didn't quote it in the PRL papers, so I was actually just trying to look back through their previous papers to draw the connections, but I couldn't quite do it in real time.
Or they might not phrase it in terms of what I call F. They might phrase it in terms of what might be called G, which is just 1 over F, actually.
That's right. Yeah,
do they have that number?
In terms of G, yeah.
Yeah, is it like I assume it's inverse, so I don't know.
It's a product of G times the field values actually at the surface of last scatter and today. So. Oh, okay. So we will have to do some decoding to read off that number. Yeah, we have to.
Right, and the field value also depends on the mass, so it's not quite as simple. Yeah.
I guess it would be nice to know, to explain that effect, how big is the coupling of the axion to E and B, because that's what they need, to E dot B. Is it a crazily large coupling, or is it actually a fairly reasonable coupling? I don't have I have to confess, I haven't looked at it.
Yeah, the term in the Lagrangian they write down is just the usual G times phi F dual.
That's right.
But yeah, the numerical regime isn't quoted very much in the PRL paper, but I think we can probably find relevant things in their previous papers.
Right. Right. So this is based on the fact that rotation, that polarizations get rotated as they travel through the axion.
That's right. Yeah.
And so the signal they are looking for, are they looking for B modes, assuming there's no B modes to begin with? How do they look for this?
No, what they actually do is they're looking for a non-zero EB.
EB, yes. Yes, I see. I see. And I guess the tricky thing is to tell if I see a non-zero EB, is it just systematic or is it right? That I guess that's a tricky thing to tell.
They have a clever method that they've devised to do this, but we can discuss it offline next time we chat.
Right, right. Yeah, it's certainly an interesting thing to do for sure.
And if I can just comment, I think that experiment is looking for a static signal, so a static rotation.
That's right. Yeah, they're looking.
So it would have to be an extremely light field that is basically static at the CMB, and then starts oscillating, which means it would have to be, I mean, as you said, the mass would have to be smaller than the Hubble constant at recombination. So then it can't be dark matter. But I mean, it's the same type of field, but it wouldn't be dark matter, right?
I really don't remember. I'm embarrassed to say, how big is Hubble at recombination in electron volts?
10 to the minus 28 electron volts.
Oh, it's minus 28. Okay, that's pretty light. That's pretty light. Yeah, then it will be, it cannot be dark matter, but certainly you could have axions like that for sure. Yeah.